Semigroups and their representations, Lecture 4, Maximal subgroups. Let us start with a quick recap of Green's relations for semigroups. Let S be a semigroup. Recall that on the last lecture we defined the following 5 Green's relations for S. First, the left relation L. Two elements A and B in S are left equivalent if and only if the principal left ideals generated by these two elements coincide. Next, we have the Green's relation R, so the right relation. Two elements are right equivalent if and only if the principal right ideal generated by these elements coincide. Then we have the two-sided relation J. Two elements in S are J equivalent if and only if the corresponding principal two-sided ideals coincide. And after these 3 relations which are defined using ideals, we also define the relation H as the intersection of the left relation and the right relation, and we define the relation D as a product of the left relation and the right relation, taking into account that these two relations commute inside the semigroup of binary relations. So we can then alternatively describe the relation D as the minimal equivalence relation that contains both the left relation and the right relation. And we have already seen that the relations D and J coincide for periodic semigroups, in particular for all finite semigroups, but in general they are different. Also, we had the following alternative description of the left relation. Two elements A and B are left related if and only if there exists element X in S upper 1 and element Y in S upper 1, such that A can be written as XB and B can be written as YA. And we have similar alternative descriptions for the right relation and for the two-sided relation as well. Now we are coming closer to the main result of this lecture, which is called Green's lemma. So here is a setup. Let S be a semigroup and let D be some D class in S. Let A and B be two elements in D which are left related. Then, due to our alternative description, there exist elements X and Y in S upper 1 such that A is equal to XB and B is equal to YA. And then let us remind that for each element W in S, we have the map which is defined by lambda W from S to S, and that's a map of the left multiplication with W. It sends an element R in S to the element WR. So this is defined for any element in S. Now we can formulate Green's lemma. The claim of the lemma is that under our setup, so we have two elements A and B in the same D class, we assume that they are left equivalent, and we assume that we have chosen X and Y in S upper 1, such that A is equal to XB and B is equal to YA. In this setup, the maps lambda X and lambda Y restrict to mutually inverse bijections between the right class of the element B and the right class of the element A. Moreover, these two bijections are compatible with the left relation in the sense that for any element R from the right class of B, R is left equivalent to lambda X of R, and similarly for any element S in the right class of A, S is left equivalent with lambda Y of S. Let's prove this statement. To start with, let R be an element in S upper 1. Then lambda X applied to BR is equal by definition to XBR, but XB is A, so this is AR, so this is an element in AS upper 1. And so lambda X restricts to a map from BS upper 1 to AS upper 1. Similarly, lambda Y restricts to a map from AS upper 1 to BS upper 1. Moreover, lambda Y applied to lambda X of BR is equal to YXBR. XB is A, so this is YAR, and ya is b, so this is br. So we have that lambda y after lambda x is the identity map. And similarly, lambda x after lambda y is the identity map. This means that lambda x and lambda y restrict to mutually inverse bijections between the principal ideal of S generated by B and the principal ideal of S generated by A. If the element B is right equivalent to some other element B prime, then we can write B as B prime R and B prime as BT for some elements R and T in S upper 1. If we apply lambda x, we get xb is equal to xb prime r, and xb prime is equal to xbt, which implies that lambda x of b is right equivalent to lambda x of b prime. Similarly, we obtain that applying lambda y to a pair a prime of two right equivalent elements outputs a pair of two right equivalent elements. So lambda ya is right equivalent to lambda y of a prime. And this means that lambda x and lambda y indeed restrict to mutually inverse bijections between the R class of B and the R class of A. So this proves the first claim of Green's lemma. Let's prove the second claim. Assume that C is an element in the R class of B. We want to prove that C is left equivalent to lambda x of C. By definition, lambda x of C is equal to xc, so we only need to find an element which, starting from xc, goes back to C. And also we can say that C is equal to lambda y applied to lambda x of C, and this is equal to y times lambda x of C. And this, due to our alternative description, implies that C is left equivalent to lambda x of C, and completes the proof of Green's lemma. Now let us briefly discuss the intersection of a left and a right class inside a given D class. Proposition: let D be a D class, R an R class inside D, and L a left class inside D. Then the intersection of L and R is non-empty. So if we fix a D class and pick any left class inside of it and any right class inside of it, then the intersection is not empty. Proof: let us recall that the relation D is a product of L and R. So it's a product of the left relation and the right relation. Take any element A in our left class L and any element B in our R class R. Then there is an element C in S such that A is left equivalent to C and C is right equivalent to B. That's how the product of two relations is defined. But then this element C belongs to the intersection of L and R, and we are done. Note that this proposition partially justifies the egg-box diagram which we described on the previous lecture. So indeed, if we draw the egg box diagram, then each row in the egg box and each column in the egg box intersects. They have a non-trivial intersection. And we can view our proposition here as a justification for this picture. Now we can list some consequences. Corollary 1. If R and R prime are two right classes inside the same D class, then the cardinality of R is equal to the cardinality of R prime. Proof: let us take some L class L inside our D class. Then there is an element A in the intersection of L and R, and there is an element B in the intersection of L and R prime. Both intersections are non-empty. But now we can apply Green's lemma to these A and B and get that there is a bijection between the right class of A, which is R, and the right class of B, which is R prime. And this proves our corollary. We have a similar statement for the left classes. If L and L prime are two left classes inside the same D class, then the cardinality of L is equal to the cardinality of L prime. So the proof is absolutely similar to the proof of the first corollary, or we can go to the opposite semigroup and just apply the first corollary. Corollary 3. If H and H prime are two H classes inside the same D class, then the cardinality of H is equal to the cardinality of H prime. Proof. Let L be the left class containing H and R be the right class containing H prime. Then they have a non-trivial intersection, and that intersection will be an H class, so let's denote it by H2 prime. Then the fact that the bijections in Green's lemma are compatible with Green's relations imply that on the one hand the cardinality of H is equal to the cardinality of H2 prime, and on the other hand the cardinality of H2 prime is equal to the cardinality of H prime. And this implies our corollary. Here is an example. So during the previous lecture we had the egg box diagram of the partial transformation semigroup PT2 on 1, 2, and it looked as follows. So we have 3 D classes, which are the same as J classes because it's a finite semigroup. The bottom D class consists of only one element, 0, which has the empty domain, so that's the 0 element of our semigroup. The top D class consists of 2 permutations, the identity and the transposition, and then in the middle we have a D class of all elements of rank 1. And this D class consists of 3 left classes and 2 right classes, and as you see, all left classes have 2 elements, all right classes have 3 elements, and all H classes here are singletons. So that's an illustration of the corollaries from the previous slide. Next, let us discuss H classes which contain idempotents. So they give us the following theorem. So let S be a semigroup and H an H class of S. Then the following conditions are equivalent. The first condition, H is a group. The second condition, H contains an idempotent. And the third condition, there exist 2 elements R and S in H, such that their product Rs belongs to H. Proof. Clearly the first condition implies the second condition, any group contains an idempotent, and the second condition implies the third condition. If we have an idempotent, then this idempotent times itself gives us this idempotent. So we only need to prove that the last condition, condition C, implies condition A. Okay, so we have 3 elements in H, R, S, and the product Rs. And we have that S is L equivalent to Rs and R is R equivalent to Rs. Then, by Green's lemma, we have that the map which sends X to Rx is a bijection from H to H. And similarly, the map which sends X to XS is a bijection from H to H. But from this, if we combine these 2 statements, it follows that for all elements G and H in our H class, the product GH belongs to our H class. So in other words, our H class is a sub-semigroup of our semigroup S. Moreover, it follows that both maps which send X to XG and X to GX are bijections from H to H for any element G in our H class. Okay, so in particular, this implies that we have a sub-semigroup. Moreover, if we take an element G in H and we map it to the transformation of H, which is given by left multiplication with G, this is a homomorphism from our semigroup H to the symmetric group on H. So we just noted that left multiplication with G is a bijective transformation of H. So we have a homomorphism of our semigroup H to the symmetric group on H. Let E in H be an element such that ES is equal to S. It must exist, because the right multiplication with S is a bijective transformation. So we can apply it to something to get S back. Then lambda E applied to S is equal to S, and any element of H can be written as S times H for some element H in H. And so lambda E applied to SH, it is equal to ESH, and this is equal to SH, because ES is equal to S. And so lambda E is the identity transformation on H. So in particular, lambda E applied to E is equal to E, so E is an idempotent. So we already proved that H contains an idempotent. Moreover, for any H in our H class, there is a unique G in our H class such that G times H is equal to E. But this transforms into the equality that lambda G after lambda H is equal to lambda E. And this means that the image of our sub-semigroup in the symmetric group on H is in fact a subgroup, because it contains the identity and it is closed with respect to taking inverses. And this means exactly that our sub-semigroup is indeed a group. So this completes the proof of our theorem. Now we can use this to describe or to classify maximal subgroups in any semigroup. Theorem: let S be a semigroup and E in S an idempotent. Then any subgroup G of S which has this idempotent E as the identity is in fact a subgroup of the H class of E. Consequently, the map which sends E to its H class is a bijection between the idempotence of S and all maximal with respect to inclusions subgroups of S. Proof: any element G in our group G satisfies that G times C is equal to G, and H times G is equal to E, where H is the inverse of our element in our group. So in particular, from this and our alternative description of left classes, we immediately get that G is left equivalent to E. Looking at multiplication on the other side, we similarly get that G is right equivalent to E, and so G is H equivalent to E. In other words, G belongs to the H class of E. So this implies that our subgroup is indeed a subgroup of the H class HE, and then the claim of the theorem follows. Next, let us talk about possible isomorphisms between maximal subgroups. Theorem: let S be a semigroup and E prime two idempotents in S. If these two idempotents are D-equivalent, then the groups HE and HE prime, so these are the two maximal subgroups of S which correspond to our idempotents, these two maximal subgroups are isomorphic. Proof: of course we can assume that our idempotents are different, so let A in S be such an element that it is left equivalent to the first idempotent E, and it is right equivalent to the second idempotent E prime. Then there are elements R, S, U, and V in S upper 1, such that A is equal to RE, E is equal to SA, A is equal to E prime U, and E prime is equal to AV. Then the maps which send X to RXV and Y to SYU are mutually inverse bijections between our H classes, and these bijections swap E and E prime. So in order to prove our theorem, we need to check that both these bijections are group homomorphisms. So we check it for the first map, and for the second map the proof is similar. So let's check that the map which sends X to RXV is a group homomorphism from the H class of E to the H class of E prime. So let's compute the product of RXV and RX prime V. So this is RXV, RX prime V. Since E is the identity element in HE and X belongs to HE, X is equal to XE. So we can rewrite this as RXE V RX prime V. Next, let us note that E is equal to SE prime U by construction. So we can rewrite RXE V RX prime V as RXS E prime UV R X prime V. Now we know that here we have E prime times UV. That's equal to E prime. So our product becomes RXS E prime R X prime V. Next, we observe that E prime is the identity in HE prime, and Rx prime V belongs to HE prime. So this means that we can just delete the E prime here to get RXS R X prime V. And now we know that SRX prime is equal to X prime by Green's lemma. So we collapse SRx prime into x prime to get R x x prime v. And now we see that Rxv times Rx prime v is equal to R x x prime v. So this proves that the first map is a group homomorphism. And similarly, the second map is also a group homomorphism. This completes the proof of our theorem. Let's discuss one example in detail. So we consider the transformation semigroup Tn. That's a semigroup of all transformations of the set 1, 2, and so on n, which we denote by n underlined. Recall that for a transformation alpha in Tn, we have the image of alpha, that's the set of all elements of the form alpha applied to I, where I is an element in n underlined, or sometimes this is also called the codomain of alpha. We also denote by kappa alpha the kernel of alpha, and this is the equivalence relation on n underlined, which is defined as follows: a pair ij belongs to kappa alpha if and only if alpha of I is equal to alpha of j. The number of equivalence classes of kappa of alpha coincides with the cardinality of the image of alpha, and this common number is called the rank of alpha and is denoted by rank of alpha. Claim 1. Let's describe the right-Green's relation on Tn. Two elements alpha and beta in Tn are right equivalent if and only if they have the same image. Proof. Assume that alpha is right equivalent to beta. Then alpha is equal to beta gamma for some element gamma in Tn. And so the image of alpha must be contained in the image of beta. Similarly, the image of beta is contained in the image of alpha, and so the two images coincide. Conversely, let us assume that alpha and beta are two elements with the same image. For each element I in this common image, choose ji and mi such that alpha sends ji to I and beta sends mi to I. Let gamma be any permutation which sends gi to mi for all I in our common image. Then alpha is equal to beta gamma, and since gamma is a permutation, beta is equal to alpha gamma inverse, which means that alpha and beta are right equivalent. We have a similar claim for the left equivalence. Two elements alpha and beta in Tn are left equivalent if and only if kappa alpha is equal to kappa beta, so if and only if they have the same kernel. Proof. Assume that alpha is left equivalent to beta. Then alpha is equal to gamma beta for some gamma in Tn. Hence, the kernel of beta is a subset of the kernel of alpha. Similarly, by the symmetry, the kernel of alpha is a subset of the kernel of beta, and so the two kernels coincide. Conversely, assume that alpha and beta have the same kernel. Let I1, I2, and so on ik be a cross-section of the equivalence classes of this common kernel. Note that both alpha and beta are injective when restricted to this cross-section, so we can choose a permutation gamma such that gamma applied to alpha of is is equal to beta applied to is for all s between 1 and k. Then, by construction, beta is equal to gamma alpha. Since gamma is a permutation, we have alpha is equal to gamma inverse beta, and so alpha and beta are left equivalent. As a corollary, two elements alpha and beta in Tn are H equivalent if and only if they have the same image and the same kernel. And also two elements alpha and beta in Tn are D equivalent if and only if they are J equivalent, if and only if they have the same rank. So now we can describe idempotence in Tn. An element alpha in Tn is an idempotent if and only if, for any equivalence class omega of the kernel of this element, the element sends omega, to some element in omega. Proof: the condition that alpha after alpha is equal to alpha is clearly equivalent to the condition that the elements I and alpha of I belong to the same class of the kernel for any I in an underlined. As a corollary, if an element alpha in Tn is an idempotent, then the H class of alpha, that's a maximal subgroup which corresponds to alpha, it is isomorphic to the symmetric group Sk, where K is the rank of alpha. So the maximal subgroups of Tn are symmetric groups, where the index of the symmetric group is the rank of the element. Proof. By our description of H classes, an element beta is H equivalent to our idempotent alpha if and only if beta and alpha have the same kernel and the same image. So the only thing which we can do, we only have the following freedom to construct a new beta. We can permute the elements of the image arbitrarily. So in particular, it means that the cardinality of the H class of alpha is equal to k factorial, where k is the rank. Moreover, if we restrict both alpha and beta to the image, to this common image, we will get that this restriction is a group homomorphism from H alpha to the symmetric group on the image, and because we have exactly k factorial elements, this homomorphism is bijective, so it's an isomorphism. This implies our corollary. In the last part of the lecture, let us talk about the Schützenberger group of an H class. So the point is that our analysis of maximal subgroups in a semigroup admits an interesting generalization to arbitrary H classes. So let S be a semigroup. Let H be an H class of S. Assume that we have some element A in S upper 1 such that A times H is a subset of H. Then, for each element little h in our H class, AH is H equivalent to H, and hence there is an element B in S1 such that B times AH is equal to H. From Green's lemma, we get then that both A times H is equal to H and B times H is equal to H. So left multiplication with A and B are mutually inverse bijections when restricted to our class H. Therefore, we can consider the subgroup G of the symmetric group on H, which consists of all restrictions to H, of left multiplications with all possible elements A in S upper 1, such that AH is a subset of H. So this group G is called the left Schützenberger group of H. Let us consider one easy example. For a non-negative integer n, consider the semigroup, actually a monoid Mn, which is given as the Riesz quotient of the additive semigroup of all non-negative integers by the ideal n plus 1, and so on. We can naturally identify the elements of Mn with the integers 0, 1, and so on n. It is very easy to see that all Green's relations on Mn are trivial in the sense that they all coincide with the equality relation. The monoid Mn has two idempotents: the element 0, which is the identity element because it's the additive monoid, and the element n, which is the 0 element of this monoid. The two corresponding maximal subgroups are trivial, so they consist of one element. And further, for each element I in Mn, the H class of I is trivial, so it consists of one element I, and so the corresponding Schützenberger group should be a subgroup of the symmetric group on one element, so it's also trivial. If the element I is smaller than n, then there is only one element in Mn which sends the H class of I to the H class of I, that's the element 0. If I is equal to n, then all elements of Mn send the H class of I to the H class of I. So this is how it works. Okay, some further remarks on the Schützenberger group. So let S be a semigroup and H an H class in S. One can define the right side version of the Schützenberger group for H using multiplication on the right, that is the elements A in S upper 1, such that HA is a subset of H. One can show that if two H classes H and H prime belong to the same D class, then the corresponding left Schützenberger groups GH and GH prime are isomorphic. And similarly for the right versions of the Schützenberger group. So this is very similar to the fact that two maximal subgroups corresponding to two H classes inside the same D class are isomorphic. And it's natural to denote the right side version of the Schützenberger group as G lower H but as a left index. Note that the defining action of both the left and the right Schützenberger group on H is transitive, so that follows directly from Green's lemma. In particular, the cardinality of both the left and the right Schützenberger groups are at least the cardinality of H. Moreover, if we have an element little h in our H class and an element A in S upper 1 such that AH is equal to H, then also 1 times H is equal to H, and hence, by Green's lemma, the transformation of left multiplication with A on H is inverse to the transformation of left multiplication with 1, so with the identity. And so this lambda A is itself the identity. And this implies that the stabilizer of each element in our H class, the stabilizer of that element in the left Schützenberger group, is trivial. And from this it follows that, so we have a transitive action with trivial stabilizer, it follows that the cardinality of the Schützenberger group is equal to H, both for the left and for the right Schützenberger group. And finally, one can show that the left and the right Schützenberger groups are anti-isomorphic, or alternatively we can think of them as the left and the right action of the same group. Some additional problems and questions at the end. Problem question 1. Provide all details in the proof that any two H classes inside a D class have the same cardinality. Problem question 2. Provide all details in the proof that, for elements alpha and beta in Tn, alpha is D equivalent to beta if and only if alpha is J equivalent to beta, if and only if the rank of alpha is equal to the rank of beta. Problem question 3. Prove that alpha in Tn is an idempotent if and only if there is a subset Y of n underlined such that the cardinality of Y is equal to the rank of alpha and alpha of I is equal to I for any I in Y. Problem question 4. Let E be an idempotent of a semigroup S. Show that the Schützenberger group of H sub E is isomorphic to H sub E. Problem question 5. Determine Green's relations and maximal subgroups of the semigroup of all partial transformations of n underlined. Thank you very much and see you next time.